Hello everyone, this is my project on investigating ant navigation using spiking neural networks and robots. So firstly, why ants? I get this question way more than you'd think, but there's a few reasons. That's not actually the reason, but some people think it is. And then there's also this reason, learn from the ant, you sluggard. That's in the Bible. That's not actually the reason though. The reason is because they're brilliant navigators. So ants on their own in a very cluttered environment, they can go over 100 meters to get food and get back. And if we can design systems that can do that, I'm sure we'll all be very, very happy. So why SNNs and robots? Well, spiking neural networks are a bit closer to the biology. So I like neuroscience, as many of you, I guess, do as well. And essentially, the neurons in spiking neural networks better mimic the actual physiological behavior you see in real neurons. They also use spikes, which are either on and off, so it's very efficient when you're building complex systems, a bit as you've heard already. And we've already heard about their efficiency increases as well. But in terms of robots, if we're able to get these spiking neural networks on robots in real-world tasks, we're able to both better compare them to real ants, but also build great robotic systems which could be helpful in lots of applications. So visual route navigation, which is what I'm focusing on, is mediated by that red object there. So that red part is called the mushroom body. And people are able to find that it's important for navigation because if you have ants that can navigate home, that's the green part, so this is on average where they're going. If you lesion the mushroom bodies, so cut them out or chemically impair them, then they have no idea where they're going. So it kind of shows that the mushroom bodies are important for this behavior. So how does the mushroom body work? So I made a model of it, and will give you a bit of an example of how it works. So let's say you put in an image, and you want to learn that image. So you have three populations, visual projection neurons, Kenyan cells, and then mushroom body output. Then if you put that image through the network, you get this about pattern of projection. You get low dimension to high dimension. And then you also have this connection which is anti-Hebbian. So that's spike time-dependent plasticity. So if two neurons spike close in time, the connection will get weaker. So what happens if you put that same image in, you get this same pattern of activation going through the network. But because this has been weakened, essentially, the final neuron does not respond anymore. So that means that the image has been learned and the mushroom body doesn't respond to anything that is familiar. So how do we use that to navigate? Well, let's say a bit more complicated example. We put a whole image into the network. Yep, so we see that information projecting through and those mushroom bodies spiking. So we can use this to say, okay, this is the first time the model's seen the image, so it's going to be spiking a lot. Whereas if it has seen it, it's not going to spike because it's familiar. So we can show it an image, learn it, and then we can rotate that. And as you rotate, then the model is going to respond more because it's seeing a perspective that it hasn't seen before. If we take that and scale that to a whole route, we can test it on lots of areas on a route, and on each point of that route, we can actually ask the model which directions are familiar and not, giving us a bunch of headings. So we wanted to take this on a more complicated data set, so we used a data set that was collected from driving a robot around Stanmer Park. And then we use that to investigate lots of different parameters to see what's important in this model and hopefully give some insight into the biology too. Now, there's a lot of results there. We're not going to go into all of them. But what you do need to know is that blue is better. So the areas that are blue are where the model performed best. And some of the important things is that you have a relatively low connection sparsity. So that's like how many connections from the visual input to the Kenyan cells. And then also, interestingly enough, training on a small amount of the data set. So what's happening here is that so if you have 100 or 200 training images, if you just train on 15% of those spaced out, the model will perform well on the whole route because it's just learning some key important parts. If you train it too much, then the model can essentially oversaturate and it can think everything's familiar. So as opposed to most networks, you need to find the optimal amount of training so that you're not saturating the model, essentially. And then this part is the part that performed the best in most cases, so we used that in our real-world experiments. Now, in that experiment, we did a comparison with two other more standard visual navigation algorithms. There's perfect memory, which is essentially just a database of images that you're doing pixel-wise comparisons against. There's Infomax, which is a small ANN, and then there's our mushroom body model. As you can see from that top there, it performed fairly comparably. The black line is the original training route, the true route, and then the 5 other lines are the inference. So it performed fairly comparably. You could even say better depending on where the endpoint is, and it was more consistent than the other models. But of course, it's not going to be perfect, which is why I will show you this video, which is 10 times sped up. It's very slow right now, but that could be improved in the future. But I think the main takeaway is that that I want to leave you with is that biologically inspired models with very simple learning rules can work in the real world. And with these models, you have to be very careful as they can be sensitive to parameter changes. And I want to say thank you to my great co-authors, and also thank you to the brilliant ants for their work and inspiration.
Thank you very much, Shay. Again, perfectly on time, so we've got time for some questions. Any questions? Julie at the front.
Hey, thank you, Shay. I thought it was really, really interesting. And I'm not a neuroscientist at all, but I was wondering whether the part you were talking about when you were saying about the using less training data rather than more training data worked better, whether there were any kind of biological parallels with that or principles that kind of would explain that from a...
Yeah, absolutely. Is this still on? Yeah. So in ants, when they're doing their learning walks, you often see that there are certain parts of the route as they're leaving the nest that they do pay more attention to. They'll periodically do a turn which appears to be turning to look back at the nest. And bees also do similar things where they do have some areas where it looks like they're trying to learn more. So it does seem that there is a biological parallel there.
More question over here.
I was just wondering, don't ants use scent marking to navigate? And so your training is on visual data?
Yes. I realize that is a classical question that I should have addressed in the why ant section. But so ants do use scent markings, but they are actually primarily visual. And we use the ants that we study are normally wood ants in rainy England, so they can't actually rely on scent markings all the time. And there's also desert ants, which are the more famous visual navigators in the ant world, and they can go a kilometer, and they can't use scent markings because it will just evaporate immediately. So they are able to use scent markings, but it's not viable in all situations. Yeah.
One more question at the back up there. Oh. Fall up the stairs.
Thank you. So are you using purely visual cues here, or are you actually trying to identify objects? Because I'm imagining an ant in real life might see objects, but then at different times of the day, it might look really different depending on shadows and these kind of things. But maybe if they're looking at and seeing it as an object rather than a collection of pixels in your case, that might add more power or more success to the way that an ant works.
Yeah, so we're doing purely visual. There's lots of data from some behavioral experiments that suggest that ants have very limited in terms of like feature identification. So if you just get an ant to train to find food, and if you put food in the same place, but then change the objects so that they're the correct relative size, the ant won't realize it's got different objects there, because as long as you make it look the same from a average outline and lighting condition, they're tricked and they think that the food is there. So I think there is some more interesting things going on in terms of like features, in terms of just the visual processing, but I think that's more kind of like low field versus wide field in the different areas of the visual lobes than necessarily discrete object localization, things like that.
I'm afraid we may have hit the end of our 2 minutes of questioning. If everyone could give another round of applause for Shay.